Well, thank you for this invitation and being part of this exciting couple of weeks for the Touching Cellulose lecture series and all the work that has been done to make this happen. So thank you for that, and also for inviting to have this or hold this lecture. To begin with, I want to come with a disclaimer saying that I will speak into the larger sort of agenda that also is the reason why we are so engaged or pay so much attention to the use of wood in contemporary architectural construction. But I will not speak much about wood, or not only about wood. I will speak about materials, bio-based materials that altogether with wood will have to sort of form a new direction in architecture, and what are the consequences from doing that. And to begin with, I will start where I ended last time when we had the small introductory lectures in April. I'll start to have to see if this works. Ah, here we go. I'll start where the overall sort of concept of tectonics, where does that sort of how do we describe it, or how do we define it, just to have everyone on board, so no one is sitting here thinking, what is tectonics all about? What does this term mean? So just to repeat what I said or explained in April, is that when we define tectonics, and I could have several lectures about that in itself, but tectonics is sort of like a part of architecture as we see it here in the triad of Vitruvius, the ancient architectural theorist Vitruvius, practicing architect and theorist, who wrote the first treatise on architecture, 10 books of architecture. He defined architecture within the three different dimensions, such as venustas, which is beauty, utilitas, which is utility or use, and firmitas, which is sort of technology or the site, the real-time sort of dimension of matter. And in that sense, tectonics is also leaning towards the firmitas, that is the relation between the material, the technique or the techniques, and thereby also the form. So in that sense, it's the little brother of architecture, you could say. But it has to do with a deep understanding of the material, its properties, and also the different tools and methods that has to be applied to treat or to work with the materials, and thereby also how the forms and the results turn out by this sort of interaction. We have in our work at CINARK, and also in the graduate program in which I teach, and I'm chairing together with Ulrik Madsen, who's also have been part of the morning program. We have been addressing or trying to define also the tectonic alphabet. It's actually one of our other colleagues, Søren Nielsen from the office Vandkunsten, who came up with this idea in part of his industrial PhD, which he started some years ago. And he defines this, as you see it here to the right, as some sort of small icons that you could say make sort of try to point out the essence of different sorts of techniques, such as the hanging, the hooking, the pitching, and so forth. And by doing this, you become more specific and more precise, maybe, about what are you actually trying to do. But as for the tectonic in architecture, we could say it then defines the correlation or the interaction between the architectural intentions and the material properties, the form principles or the anatomy of the structure or the construction, and thereby also the choice of building technologies and techniques, and finally the structural rules present in construction. So it's about the specification and designing and joining of materials, and how they form an architectural synthesis. And thereby it also holds or addresses the dimension of architectural ethics. It's a way to direct and control resources in construction. But before I return back to the question of tectonics, I'll start in a different sort of setting. And as I mentioned earlier, this presentation or this lecture is I'm trying to draw a bigger picture that also sort of you could say also engages some of the ideas or sort of the overall technological development as also presented by Herman Blumen this morning, but in a different way, in that sense that we also have to look at the different materials and technologies as a you could say a catalog or a diverse way of also looking into new structures and new sorts of architectural articulation. And why do we have to do this? That's because of this ecological crisis we are facing. It's not only a climate crisis, but it's a much larger critical situation we're looking into, and we see now that at many levels. So we see these critical global challenges across biodiversity or lack of biodiversity, increasing waste problems, and also the question of material scarcity, and not the least the climate crisis that also affects different areas of the world where we can build, how we can build, and by which sorts of materials. And the question about material scarcity, of course, is also a question that is very present when we speak about wood, because we see different industries also saying that it may be a problem if we can, or question if we can supply the construction industry with the amounts of wood that may be needed in the future. And that's also what I'm trying to address here, that we may have to supplement the material wood with other sorts of bio-based materials in order to be able to reach the goals we have to reach. So as for the ecological crisis, the building and construction industry actually has a very high impact on the different numbers. We see that the total energy consumption comes from the construction industry by 35%. And we're also responsible for 40% of the greenhouse gas emissions. We're also responsible for 40% of the total material consumption. And in the EU, we have about 30 to 36% of the total waste. All this together, we have to look into in different ways, but at the European level, we have decided that in 2050, we have to have a full reduction of 100% of the greenhouse gases of the CO2 emissions. And in Denmark, the present government have decided that within the first or the next 9 years, we have to reach a reduction of already 70%. And that is because they say that this is something we can reach pretty quickly, and by means and ways of changing procedures that we can reach these goals. However, colleagues of ours that are engineers, researchers at the Southern Danish University, they look into these sort of numbers and they say, well, in case or in order to reach these sort of ambitious goals, we have to work from the you could say an overall understanding of our planetary boundaries, and thereby having to define what we could call some sort of absolute sustainability that sort of not reaches beyond the planetary boundaries, but that actually helps us to provide different sorts of solutions that you could say reach these numbers more realistically and actually shows a very quick sort of change. So what they have done by studying standard family houses in Denmark, a large number of standard family houses. They've said in order to reach these goals, we have to reduce by 90 or 89%, we could also say 90% of the harmful environmental effects of construction. And we have to reduce by 80% of the greenhouse emissions from energy consumption. And finally, we have to reduce the living space per person by 60%. And these numbers they have worked on, or how do you say, come to the surface by having studied these different ways of existing construction and then comparing it to the planetary boundaries and saying that this is actually what we have to do in order to act, you could say, safely within this understanding of not having the temperature rising beyond the 1.5 centigrades. In order to do this, we need to look into construction and the way we use materials and the sorts of materials we apply, but also, of course, as the final point says, the overall spatial consumption. I mean, how much do we build, and for whom, and for how many? And today we see in Denmark this sort of new movement that is called tiny houses, and here's one of the examples of that. Some people believe that living in very small houses, only taking up the minimum space for themselves, and also having solar panels and biking around, that's maybe the way to get about it or get around it. But at the same time, in case you could say if all people around the globe would do the same thing, there would not be room enough for everyone. So we have to find ways to engage in these sort of questions by a number of different approaches. So if we look into you could say the question of absolute sustainable architecture, we have in our research centers tried to see what does this mean and how do we actually go about it. So we tried in 2017 to use what we in Danish, a Danish saying is that we take our own medicine, in that sense that if we do have to reduce by these radical or high numbers, and we had to reach a different way of construction by other sorts of materials, what can we then do? So we were asking ourselves these questions. I mean, how can we design architecture and build according to absolute sustainable principles? And what are the consequences for the use of materials, for the building techniques, and not the least the tectonics and architecture? When doing this, we came to three main materials we wanted to look into, which actually ended up being the only one we could more or less apply. We wanted to test this according to both an overall understanding of the material themselves, the material properties, but also as for you could say the crafts tradition and the building culture, but not the least how we could also scale it up according to contemporary construction industry and the manufacturing systems and procedures that are applied there. So what we did was actually we sat down and wrote what we call the Manifesto for circular construction. We very quickly found out that in order to reach these goals, we also had to make sure that the materials applied would stay in circular loops in terms of reuse and recycling. So that's why the sort of the circular concept also came to play. And this is only part of the manifesto. So we knew we had to sort of, and I'm going to put it in the opposite order. We had to leave out materials that would demand great amounts of non-renewable energy in the production, or that had a severe negative environmental impact. That would primarily be materials made of raw oil that are synthetic, and materials that are damaging to the health of humans, animals, and nature. In addition to this, we knew we also had to minimize the amount of material and the number of different materials in constructions, and not use contaminated materials without additional treatment. Use construction joints that could be disassembled, and finally try to reduce waste in production. So part of this manifesto also was generated on the background of this small, what we call the construction material pyramid. And this is actually the second version. There's one primary to this. But it was developed in order to find out, well, if we have these different sorts of materials and we calculate the CO2 footprint by per kilo, how does these different materials actually perform in terms of the CO2 emission? And this sort of these materials very quickly were some that didn't have negative effects, or negative in that sense that they were harmful to environment, and also that they were applicable in many different ways for what we could call basic wall constructions. At least that was what we wanted to try to test. But we also see that we have the metals or the insulation materials in the very high top of the pyramid. And that was, of course, I mean, materials we also know from contemporary construction industry, that we wanted to see, okay, in case they're part of the larger picture, how little can we use it, or can we replace it by other materials? On the you could say on the background, or on I mean, following up on both the manifesto and the construction material pyramid, we defined this sort of strategy for what we call the radical tectonics, that we wanted to use these pure materials, basically hardly not treated or manufactured into, so you could say, other levels of refinement. We wanted to use the dimensions, the measures dictated by industrial standards in order to eliminate waste, and the least possible degree of processing of materials and components in order to minimize the amount of energy in manufacturing. We wanted to use reversible joints in order to retain or salvage the different materials or components for further use, and also have these very simple assembly and construction details, all of it together for the low CO2 footprint, and applying what we could call the standard components and only few custom-made adapted components. And we want to apply these clear tectonic principles and have, or pay attention at least also to the thermal properties, although this was not about, you could say, it was not a full realistic sort of or realizable maybe construction. It was a test of this sort of radical tectonic idea within the scheme or the overall theme of absolute sustainability, or absolute architecture, sustainable architecture. So we continued testing or trying these, what we call the radical tectonic experiments, and we did that in these three different main materials. The first one was the wood prototype, where we developed this prefabricated module insulated with wood fiber. And very important here is that we didn't do the you could say the crafted joints of wooden elements, which is often applied. We screwed the whole frame together in order to be able to dismantle it again, and also had these specific small you could say joining elements of metal. So we had a very clear you could say priority in terms of what sorts of materials did we apply for what purpose, and what was the amount of material within the structural element. That sort of you could say calculation or design strategy was part of the work all the way through. And in order to do that, we also applied what we could call the tectonic alphabet. You see it here to the left, as a way to sort of optimize and also how do you say, categorize the different sorts of structural elements to make sure that each of the element was applied in the best way of its you could say how it's situated in the structure, and for its and due to its specific properties. So we came up with this wall element that was assembled with these joining brackets, or you could say it's like a key lock that locked the elements together across a cork plate. The second wall was made of unburnt clay, and with the poor tone clay block as the main structural element. So in this case, we wanted to use a very highly finely refined construction element as the poor tone Ziegel block, or what's it called, brick block. It is in that sense you use less energy to burn these blocks, and you have a higher sort of a higher performative outcome. In that sense, you have instead of putting up one brick after the other, you have these larger blocks that can also be assembled without any mortar in the vertical joints. And in that sense, we eliminate or rather increase the insulation of the block itself. At the same time, we know it cannot stand outside in the weather, so it has to have some sort of cover, either plaster or brick cover. And in this case, we tried to test it together with the unburned brick, but also with reused bricks on the other side. And it turned out to become this what we also call the braided wall, because we wanted to apply original brick procedures and brick techniques in order to make the structure stable, rather than using what we do today in contemporary construction. We use steel rods or steel bonds between the inner and outside walls. The final wall was made of straw, in which we used straw bales that were sort of stacked or put on top of each other, and they have a hard time standing by themselves, so they had to be reinforced with these steel rods. But also they were sort of made in this layered structure of wooden, you could say wooden frames that would also sort of make or divide the surface up to you could say in panels that could be treated or even plastered with clay mortar or plaster on the top. That also in order to be a fire hindrance. And this structure was also ended up as, you could say, like a fundamental sort of low emission structure, where it was particularly the question of the cladding and the fire protection that was part of the main issues when defining and designing this particular construction. So what was sort of the overall aspect of these three experiments was that we were concerned about what we call the reversible joints. They are important in order to take the structures or construction apart, and also take each material within each their fraction to be reused, or as larger modules. So these sort of joining elements, we we have pointed out that they could be envisioned as tectonic motifs. And by having this disassemble strategy, we also facilitate maintenance of the structure. You can take either certain parts, smaller parts out, or you can actually disassemble the full structure. Also, we wanted to separate what we could call the life cycle of the building from the life cycle of the materials. In that sense, if we apply similar strategies or building techniques in renovation, for renovation of architecture, we can then just how do you say, renovate parts of the building. We don't have to tear down the whole building. So it's also a way to sort of categorize or divide the different parts of the building into long-lasting elements and less more, you could say, short-lived elements. And finally, we wanted to point out that this whole way of working with the different materials and their properties and the structural and construction performative characteristics, it points at this ethical awareness we have to have as for the choice and use of the materials, but also the cultural dimension in terms of taking existing or traditional crafts and trying to translate them into contemporary industrial production. As for the three walls, we also analyzed them. It actually was retrospect. So this was an experiment that was came from the Manifesto and grew over the practical experiments. And finally, we went, you could say, we went back and analyzed the different wall structures. And you could say this is just showing that how the different materials, the amount of the different, the percentage of the different materials applied in the different structures. We can see, as for the wood structure, the wooden fiber insulation is the largest amount of the material used, whereas the cork sheets is the less amount. Whereas in the clay structure, we had the insulating block, whereas the clay and clay mortar and salvage brick actually have almost the same, pretty much the same amount. Whereas the straw bales or the straw structure, of course, the straw bales was the largest. You say that the greatest amount of material that was applied. Then when we looked at the CO2 emissions, or the greenhouse gas emissions, it was very interesting for us to look at how the CO2 footprint per cubic meter was looking pretty much as we expected according to the construction material pyramid. So if we look at the first diagram to the left and the top, we look at the processed steel. We can see it has a very it's situated in the high end, whereas both the wooden profile, the OSB, are in the very low end, or you could say in the minus. Whereas if we look at the proper structure as built, and we look at the square meters of 1 square meter of the structure, we see now that the processed steel is moving towards 0, but yet we still see that the solid wood is performing very well, whereas the OSB is now moving towards a higher CO2 emission. So what does this tell us? It tells us that it's not just about the different materials you apply, but it's also, I mean, what sort of additional materials to apply, and what is the amount of the material applied, which is having a great impact or affects the CO2, the final CO2 footprint. Also, we looked at the different life cycle scenarios in terms of the different structural materials, how parts of the structure could last for long, whereas other parts would have to be exchanged or taken out or even demolished, and how these different materials could be reapplied or returned to either some sort of technological reuse in that sense in the construction industry, or go back into the natural processes in nature. And when we're dealing with bio-based materials such as wood and unburned brick or clay and straw, of course, it has a very high possibility to go back to nature without harming the environment or nature and so forth. Whereas the high processed elements and products or components, they can stay in the loop, in the technological loop, and also have to be, you could say, reharvested and reapplied without being altered or changed. So this experiment altogether told us a lot about how these different ways of processing and how the structure itself has to be thought out and designed is very, very important, and has to be planned very in great detail in order where you can go back and actually reharvest the different materials in a proper, you could say, absolute sustainable manner. So what we see here to the left is how the different structures at an overall level had the CO2 emission per kilo structure, where we see both the wooden and the straw structures of I was going to say, of course, but go beyond zero, and whereas the burnt brick and the reused brick or brick block is performing or having high emission. But as we say, it goes to beyond zero. This is an ongoing discussion, as many of you probably know or is part of, because many voices in the construction industry says that it's not true, because the wood itself, as soon as it is taken out of the structure or burned, or it's deteriorating in one way or the other, the CO2 will be emitted into the atmosphere. However, as long as we can keep these bio-based materials in the structures and in the loop of reuse, the better. Because as for the you could say the overall requirements presently, where we have to have these high CO2 reductions, it's important that we apply these sorts of materials in order to reach the reductions. And I'll now return very shortly to the construction material pyramid, because it has become a tool and a way of thinking, which we are still working on within our center. And it has been developed into a digital format now. And you can go to the site, which is written down here, materialepyramiden.dk. That's where you can find it. And it's actually programmed in such a way that in case you are outside Denmark, it should translate directly into English. I don't know if it translates into German, but at least it does into English. This is not an interactive image, so I cannot push the different buttons and show you how it works. But as you see here up to the upper left, we have these different environmental impacts, and we have different sorts of impacts, also the global warming potential. We also have ozone depletion and water, what's it called, acidification, and some of the 5 main environmental factors that are harming, you could say, the ecological balance of our planet at the moment. Then we have here the kilos or cubic meter, two different measures. And then we have different material groups, so you can select either insulating materials or structural materials, and so forth. And finally, in the functional device refers to sort of main structural features such as the pillar or the wall, and so forth. And we have now added 60 materials to the pyramid, and we try to keep it this way, because then we can still have an overall, I could say, an overview of the different materials, although we have many people or companies actually writing us if we can add more materials to the pyramid, because they want to be part of it with their different sorts of products. But what's important for us is that it's not, we don't want to showcase different products and how they perform in terms of their environmental impact, but we want to also look at the basic sort of materials. So we also apply the numbers and the data from the Ökobaudat and the EPDs across different companies in order to use, you could say, more standardized measures. So we haven't sort of invented anything here. We have just invented a way of sorting and displaying how these different materials they act according to their environmental impact. And just to mention this very shortly, that of course the construction material pyramid also sort of taps into this overall what we could call the sustainable lingo, which is connected to materials in general. And as I just mentioned, we have the environmental product declaration, which is linked now to most of contemporary or today's building materials, and how they are performing according to these different measures I was mentioning beforehand. This is also a standardized way to be able to compare materials across different countries, and different. This is particularly in Europe, you could say, but also across different sorts of manufacturing places. So then we have what we see now, the ISO 14025 analysis. It's also about the environmental impact of production. So this ISO, there's an international standard that's also being applied across material production. And then these two, you could say, these two ways of standardizing also is part of the larger sort of life cycle analysis a scheme that has been developed over the past couple of decades. And that is now also being supplied with what we could call the life cycle cost, where there's an intention to try to look into how much are the costs of these different sorts of materials and their dependencies on one another. And then finally, we also see various certification systems or standards such as the DGNB, the BREEAM, and the LEED, which are defined from different, you could say, national standardization authorities, where the DGNB comes from Germany and the BREEAM comes from the UK and the LEED from the US. And it has been actually multiplied by numerous additional certification systems across the world. I think most larger industrial countries have these sorts of systems. But if we return to the building material pyramid, it works in that way that at the bottom of the larger pyramid, we see this small, what we could call the calculator, in which you can choose if you tap the different materials on the pyramid. it goes directly into the calculator at the bottom of the screen, and here you can then define the different amounts, depending on if you know the volume or the cubic meter, or the square meters, or the millimeter of a certain material. And then it then calculates what you could call your own pyramid over here. So in this case, I tried to put in different numbers to see how it turns out if we have this sort of distribution of materials, and we will then have a negative CO2 footprint. So the construction material pyramid, you could say, is a way to show and actually display different sorts of materials. I mean, not to say that slate is less, how should I say this? Is less harming than wood, or vice versa. It's rather a question of showcasing the different materials' environmental footprint in different ways, and by this sort of serving the architect or the construction manager, the carpenter, or whoever, to be able to make a more, you could say, informed choice between the materials, and also in order to be able to discuss with the client or with the colleague if you should go with one solution rather than the other. So it's actually not meant as a way to sort of come up with any answer to how to do this right or wrong, but it's rather a way to, or it's a tool that is made for ways of looking into the consequences of your material choices. So in that sense, it's rather, you could say, a tool for questioning rather than it's a way to answer to whatever problem. We do know now that a lot of people use it in different ways, and we also know that some people use it as a way to supply their design with this sort of data or this sort of information, and we do think that it's, in that sense, it works very well. And we have also had a lot of criticism from the Danish construction industry, in particularly from the you could say the high energy consuming industries, that it is sort of misleading customers or people using it, because they think that only the bio-based natural materials are to be used in the future or in construction in general, whereas the burnt brick and the concrete and the steel and the glass, we shouldn't apply that in the future. And of course, we know that's not possible, at least if we have to live in you could say in houses and cities as we know of today, in one way or the other. But of course, it does question the fact if we are going to use the sorts of materials which we have been used for the past 200 years in the measures or the amounts as we are today. So what the construction material pyramid is trying to do is actually not to offer any sorts of life cycle analysis. It does apply what you could say the first 3 phases of the life cycle analysis scheme, but it only shows how much CO2 is applied until the very moment you have the material on site and you are ready to go and build. We don't say anything about, or the construction material pyramid doesn't say anything about what happens when this building is or the construction is designed and finished, and is it done properly, and what is the lifetime of the various materials in the structure, because that's a completely different that's a completely different setup. So we are only looking at the material environmental impact. So what do we then do as part of this, or how do we bring this sort of knowledge into the education? Of course, we do that by different means, and but one thing we have developed over the years is what we call the research and innovation module, which is part of the 5th year of the architectural or the graduate program, Settlements, Ecology, and Tectonics. So over the past couple of years, we've also studied as part of this what we call the radical tectonics. This research and innovation studies or innovation module, as I mentioned before, it's what we could call a collaborative module with partners from or in construction industry. This example I've chosen to present today is not about wood. We haven't had any module with where we had I mean, you could say a specific study of wood, but we have had what wood has been part of many of the different studies, in particularly also in what we could call the circular economy projects, where we have a lot of wood also being taken down from demolished buildings, and that can be reapplied in new structures. But what I'm going to show here is actually the example from 2019, where we were working together with the Thatchers Guild in Denmark, and in order to find out and you could say discuss with them different ways of applying straw, or what you could call reed, which is applied for thatching roofs, but also can be applied for thatching facades, because the Thatchers Guild, which is a very old guild of craftsmen, have over the years seen a growing attention or interest in applying reed in different ways, and they want architects also to be more engaged with sort of pushing the boundaries in terms of by which means and for what purposes can we actually use this material in architecture. So we had this 2.5 months where we worked together with the Thatchers organization, and the students were directly presented to the different craft techniques by some of the you could say the high-end thatchers who also train the apprentices at the school of thatching. And here we see some of the students who are now trying to test and experiment with the proper craft techniques. We were handed over a great number of reed bundles of reed, and it was sitting in the studio, and the students were directly confronted with it at a daily basis, and they tried to sort of engage with the material directly, also in the various projects. They worked usually in settings or groups by 2 people. We only had very few students working on their own, and then they were also grouped in larger groups of 5 or 6 students, where they also talked about their different projects across different experiments. What we see here is actually one group that was trying to test the reed in different sorts of where they grinded it and boiled it and tested it as a you could say some sort of bio-based brick, or also its structural properties. Whereas the other image to the left, we see experiments in terms of also having it as a cladding, a regular cladding for vertical structures. And as you see here, we at the studio, we had the reed sitting all over, and the group we see to the left were actually testing if we could, if they could take the you could say the waste product from the reed and form it into these different compressed bricks that could be applied either for as a brick or as a cladding panel. And we had several other projects, and as you see here to the right, we had a small exhibition in the hallway of our building, in which some of the different projects were displayed. One of the projects was also engaging into the question of if we take a regular building as we know of today, which is this project is actually is about to be built or has been built, and is designed by one of an architectural office called UNV, together with another architectural office, Danish office called Yaya Architects, and together they have designed these social housing projects. So this group of students took these social housing projects and tried to test the fact that what would happen in case they clad these are actually wooden structures, you could say box module structures in wood. What would happen if we clad these wooden modules with reed, and what will be required in terms of in particularly also what we tested in the straw bale structure as for fire, you could say fire protection. So they actually came up with you could say almost like a new architectural language, in the sense that they took the ground floor and pushed it further back, and in order to have you could say an escape way in case people run out of the building. You don't want to have burning material falling down at you, so you would have to be able to run from the building. But they also made these sort of hoods around the windows, so in case you were to be rescued out of the window, you would not be neither you would be harmed by a material that maybe would fall down across the facade. They also tried and tested different sorts of mineral materials, such as clay, chalk, lime, a specific Swedish paint that's also a mineral paint, as a way to cover or impregnate the reed, so it wouldn't burn as easily. And then they also made these fire tests outside here outside our studio building, in order to see how it actually reacted to fire. And they came up with, from these very you could say early experiments, they came up with already some results that showed very quickly that the element, as you see from the how do we see the second from the top, which is treated with clay, that it took some time before it actually started to burn. So how do we then research in this field of radical tectonics, and how do we bring some of these all of these different ideas together? We now have applied for a project from the the Ministry of Environment, where we can apply for money that actually can be used across construction industry, research institutions, and you could also say test institutions. So we applied for a project where we wanted to test some of the ideas also presented in the students project, facades, vertically thatched facades with CO2 neutral fireproofing. In this case, it is clay. In part of the project is also based on, you could say, historical studies of traditional building in Denmark and the southern part of Denmark, in the northern or northern part of Germany, because we have found in old manuals of you could say building manuals that there are references to clay as a fire retarder or a fire proving material, together with bio-based materials such as thatched structures. And what we see here is actually the Pilisca watermill, which is originally from Bornholm, the small island in the south of Sweden. It's part of Denmark, and this small house actually has clay, as you may see, on the very top of the roof, and the clay washes out down over the roof, and in that sense, it's also it protects the roof for in case of fire, but it may also have some other sorts of you could say impregnating or protecting properties as for the reed. We have now made a very sort of specific study of different sorts of materials. We sort of brought some of the ideas also from the students project further, but also wanted to test it in regular thatched structures as we know of them today. So we made these different experiments, altogether 14. And we see now here actually the guy in the middle with a ponytail. He's the head of or the chair of the Thatchers Guild in Denmark, who's also now involved in the project. And the guy with the cap, he is Dutch, Ruud Koning, who also was one of the main thatchers of the Vadehaus Center, a very well-known or famous museum designed by Dorte Mandrup, which is right next to the flatlands of the west coast in the southern part of Denmark. So it's a very good group of people who have engaged in this project, and what we see here are small fire tests that had to be developed first in order to be able to scale it up for larger structures. And we have all the 14 elements all together with the different sorts of impregnation and how they are burned. They're actually exposed to fire for 20 minutes. So the material itself really has to be fully, you could say, covered in clay, but also it shows if it has any effect when it's exposed to the flames for such a long time. So what we see here is actually one of the elements that has been fully covered in clay, and how it does get black and it does sort of charcoal on the surface, but it doesn't burn. And these are the same 14 elements all together, where we see the one to the far left, which was an untreated element, is almost gone, almost burned away. Whereas we see the fourth from the left, and the final one, and the third from the right, that all have been covered in clay in one way or the other. That they actually perform very well. So now we're in the process of scaling up of the different elements, and also wanting to test it together with other materials. In this case, we have not only covered the reed itself, but we have also, what you see here to the right, added this a clay plate. It's actually a Claytech plate that becomes part of the structure. And it's actually to make what you call a fire stop, where the flames, if they crawl all up over the facade, it sort of makes a different sort of movement in the flames, and therefore it also hinders the fire to grow quickly. So these were the three main elements. The one you see on the image to the right, standing to the left, is an untreated element, a regular thatched element, whereas the two other ones, we have, you could say, a regular one that is covered in clay to the right, and the one you see to the far right has this sort of fire stop with the clay plates also integrated, also making this sort of horizontal line. And this is being burned with the gas flame for 30 minutes. And then we see now here to the right how it actually, after 30 minutes, of course, it does start to burn because it heats up, but actually it doesn't burn away as an untreated element would do. And now we are working on what an exhibition that is going to open here the 7th of October. It's called 70% Less. It taps directly into the overall political agenda of our government. And we are going to present the structure as you see here. It's just some early images of a full-scale structure in 1:1, where we want to present how this structure is being treated in different ways. As for the you could say the load-bearing structure in the back, we are now at this moment planning to have what we call the eco cocoon. How do you say, industrially manufactured straw bale element. It's a prefabricated straw bale element where you could say the different materials are applied for the most sort of high performative characteristics, such as the wooden part of the structure is applied where it's supposed to strengthen the less you could say the materials that have a less load-bearing capacity. So in that sense, we have tried to sort of optimize or focus the different material properties for the different the application purposes of the structure, but also as for the architectural design. So this is the final image, and this is just to try to wrap up or where to get started. I think one of the main conclusions is that when we look into contemporary or future construction industry and architecture, we have to realize the fact that it's all about ecologies and all the different sorts of materials and actions we do in terms of how to engage with materials is connected in one way or the other and have consequences for each other. So we have to have this ethical understanding of our material resources. As for, you could say, an architectural approach, it's about choosing an overall strategy. We have to focus on a specific, you could say, specific materials, or specific ways of dealing with the materials in order to either being able to harvest them again later when they have been sort of serving their function in the structure or in the building. And a way to focus could be, as we did, we started out writing this manifesto, and one thing took another, and we ended up making the construction material pyramid and also having this ongoing one-to-one testing parallel to this. So it's also about defining the principles, I mean, by which design rules and fabrication methods are we working. And as for the design rules, I would like to emphasize again the Tectonic Alphabet, which is very applicable and also in many ways very specific. So it's a good way to sort of navigate in terms of where do we start and how do we actually design with you could say a radical tectonic approach. And then finally, we should cherish the world of details. as in the final example, showing you that how this whole understanding or trying to, or the study of the reed and how it can be reintroduced in contemporary construction as a, you could say, a supplementary material together with wood and other bio-based materials. We now learn that the details themselves have great importance in this case in terms of how to hinder the fire to develop in the structure, as we saw when we had the clay plates integrated in the facade panels, but also as a way to think about, as in the early examples of the three wall structures, how we can disassemble the different materials and modules. So it's just a matter of using your fantasy, draw and test, and test in full scale. So thank you for this, and I'm looking forward, or we're looking forward to follow the touching cellulose workshops the next couple of weeks. Thank you.